Hello everyone, welcome to our ICASSP 2020 talk. My name is Herman Kamper. My collaborators on this work are Yevgen Matusevich and Sharon Goldwater. Let's get into it. Despite advancements in recent years, current speech recognition systems still require large amounts of labeled speech audio datasets. Prompted by the observation that infants actually acquire a language without any transcriptions, researchers in the zero-resource speech processing community have started to look at methods that can learn directly from unlabeled speech audio. A number of tasks have been tackled. This includes things like unsupervised term discovery, where you're presented with a collection of unlabeled speech audio and a method tries to discover recurring words or phrases in the unlabeled data. In query by example search, a system is given a spoken query and is then asked to retrieve utterances in a speech collection that contains instances of that query. A lot of these zero-resource speech applications normally boils down to this problem that you need a method that allows you to compare speech segments, and normally these segments can be of different durations. The classic way to deal with this is to use a method like dynamic time warping to align the segments, and then you can use the alignment cost. However, this can be slow and is also sometimes inaccurate. And that's why acoustic word embeddings have been proposed as an alignment-free method. So the idea is that we take a speech segment like this one, and irrespective of its duration, the number of frames in that speech segment, you want to represent that speech segment with a fixed dimensional vector in a fixed space. So this segment here, for instance, might be mapped to this three-dimensional vector here, while the segment here at the bottom might be mapped to this vector at the bottom here. What we want from our acoustic word embedding method is that if these two segments are instances of the same word, we want the distance between their embeddings in this fixed dimensional space, we want this distance to be small. While if these two segments contain words that's different, then we want this distance to be large. The point is that by mapping a variable duration segment to a fixed dimensional vector, we can easily compare these two segments by simply calculating a distance in this fixed dimensional space, and that's a lot faster than doing alignment. There's a growing body of work on different acoustic word embedding methods. Both supervised and unsupervised methods have been explored. Unsupervised methods are particularly useful because they can be applied in zero-resource settings. Unfortunately, there's still a large performance gap between unsupervised and supervised methods. As an example, this is some results from a previous ICASSP paper. And what we see is that if we do use labeled data to train this particular acoustic word embedding model, then the performance is a lot better than when we are in this unsupervised case. So a big motivation for the work presented here is this question of whether we can use supervised embedding methods but still apply them to a zero-resource language where we don't have any labeled data. And our approach will be to take labeled data from a number of well-resourced languages and then use that labeled data to train a multilingual model in a supervised way. We will then take that multilingual model and apply it to zero-resource languages for which we don't have any labeled data. The question then is whether this kind of transfer learning approach, whether that works better than just training an unsupervised model on the target zero-resource language, on that unlabeled data that we have. So to answer this question, we will compare a few state-of-the-art unsupervised acoustic word embedding models to multilingual supervised embedding models. The first unsupervised model that we consider is an autoencoder recurrent neural network. So we've got some unlabeled speech audio, and we can grab random segments from the speech collection. And if we pick this segment, for example, then that serves as the input to an encoder RNN. The encoder RNN then outputs this red vector here, and that's our acoustic word embedding. And the model is trained with a decoder RNN, which tries to reconstruct at its output the same frames as at the input. At test time, we will throw away the decoder part and just use the embeddings produced by the encoder RNN. The second unsupervised monolingual acoustic word embedding model that we will consider is the correspondence autoencoder RNN. This CAE RNN actually works in two steps. The first step is that you apply an unsupervised term discovery method to your unlabeled speech data in your zero-resource language. And this unsupervised term discovery method proposes pairs of segments which it predicts to be of the same type, it's the same word. And instead of trying to reconstruct one of the items, the correspondence autoencoder RNN is trained taking one of the items as the input, and then it uses the other item in the pair as the target output. And again, we've got this intermediate embedding, and at test time we throw away the decoder part. Now we turn to supervised multilingual acoustic word embeddings. So here we've got a collection of labeled speech audio from a number of well-resourced languages. In this example figure, we just have labeled data from Russian, Polish, and French. And as our first method, what we do is we simply train a classifier RNN, and we train this model jointly on the data from all of these languages. So we train the model, it's a RNN, it takes in an isolated word. The model outputs embedding, and then we've got a shared output layer here, shared across all the languages, a softmax layer, that tries to predict which word was presented in the input. And in this way, we hope that the encoder here captures properties that are common to all of these languages and will hopefully transfer to a zero-resource language which it hasn't seen. As our second supervised multilingual acoustic embedding method, we train a CAE RNN again, but instead of using discovered words, as we did in the unsupervised case, we now just use ground truth words from our set of well-resourced training languages. For our experiments, we use data from the global phone corpus. We use 6 languages as well-resourced languages, and we use their labels to train our multilingual models. As our evaluation languages, we treat 6 other languages as zero-resource. We pretend that they don't have any labeled data. For evaluation, we use the same different task. This is an isolated word discrimination task that was developed specifically for figuring out whether a representation is able to say whether 2 segments contain the same word or different words. The metric that it outputs is average precision, the area under the precision recall curve. For all of our models, we use an embedding dimensionality of 130. We consider 2 baselines. The first is downsampling, where we simply keep 10 equally spaced MFCCs from a word segment, and then we flatten that into one vector. As another baseline, we consider dynamic time warping alignment between the full segments to do this same different task. In our experiments, we try to answer 3 concrete questions. The first question is whether multilingual supervised modeling outperforms monolingual unsupervised modeling. This bar plot shows test results on Spanish, with average precision given on the y-axis, higher is better. The AE-RNN isn't shown here because on development data, the CAE-RNN just performed a lot better. As we've seen in previous work, we see that the CAE-RNN outperforms the kind of naive downsampling embedding approach as well as dynamic time warping. But more importantly for us, we see that the multilingual models, both this multilingual CAE-RNN and the multilingual classifier RNN, both of them outperform the CAE-RNN and the unsupervised monolingual model. So this model was trained on unlabeled data from Spanish, but we see that that doesn't work nearly as well as training a multilingual model on 6 other languages, not Spanish. Comparing the CAE RNN to the classifier RNN, on Spanish we see that the CAE RNN actually outperforms the classifier RNN, but this trend is not consistent over all the evaluation languages. So if you look at some of the other zero-resource languages, and the classifier RNN sometimes does better. So for example, on Hausa, the classifier RNN does slightly better. But importantly, on all 6 zero-resource languages, the multilingual models always outperforms the best unsupervised model trained on the target zero-resource language. The second question we ask is whether training on more languages help. So here we're looking at development results on Croatian. We first just train some models on label data from Russian. Then we train supervised models on the combination of Russian and Czech. Then we add French. And finally, we just look at the systems trained on all 6 languages. Here we show results both for a CAE RNN and a classifier RNN. And just for comparison, we also include a CAE RNN and a classifier RNN, both trained in an unsupervised way on Croatian UTD words. What we see here is that there is a general upward trend as we add training languages, but this can differ a little bit based on the model. So for example, for the classifier RNN on Russian, if we add Czech, then we get this very big improvement. These trends are slightly different on some of the other zero-resource languages, but one thing that's always the case is that training just on Russian always outperforms the unsupervised monolingual systems trained on the target language. The other thing is that generally adding the second training language leads to some improvements, but then after that the systems tend to generally plateau. Finally, we ask the question whether the choice of particular well-resourced training language is important. Here we look at a number of supervised monolingual systems trained on each of our well-resourced training languages. In this case, in all cases, we considered supervised CAE RNNs. And what we do is for each of these supervised monolingual systems, we apply them to all 6 of our zero-resource languages. The colors are normalized per column here, so per zero-resource language. And what we see here is that the well-resourced training language can actually have a quite large effect on the performance on a downstream zero-resource language. For example, on Spanish, using a supervised system trained on Portuguese, that system gives the best performance. Similar on Croatian, the Czech system gives the best performance. Some of the trends are a little bit hard to understand, but there's 2 things that's important to note from these results. First, if we compare, for example, the results from the supervised monolingual systems on Hausa to an unsupervised system trained on Hausa, then you will see that irrespective of the well-resourced training language, the performance here, all of these numbers will be better than an unsupervised Hausa system. And that's actually the case for all the training evaluation language pairs in this whole plot, apart from the Spanish-Thai combination. The second thing to note is that the multilingual CAE RNN, the one trained on all 6 of these languages together, also does better than any of the numbers on this plot. So in conclusion, we found that this transfer learning approach, whether you're using a multilingual CAE RNN or a multilingual classifier RNN, this approach outperforms unsupervised acoustic word embeddings trained directly on the zero-resource languages. There are still a number of unanswered questions. One of the reviewers noted that Siamese models are used most often for getting supervised acoustic word embeddings, and we didn't look at that. The results also seem to indicate that there's to some extent little to distinguish the multilingual CAE RNN from the multilingual classifier RNN, so further analysis is required to understand the difference between these 2 models. The code for this paper is online. You can go and look on my GitHub page and find the code there. I should add that after the camera-ready paper was due, we found a small bug in the code that we've since fixed, and this presentation contains the most recent results, but just keep an eye out for an update on arXiv as well. I hope you enjoyed the presentation.